we left off in section 8.2. So the next thing we need to talk about in section 8.2 is another vector operation called the dot product. So if u is the vector u1, u2, and v is the vector v1, v2, we say the dot product of u and v is denoted u dot v and is found by saying u dot v is equal to u1 times v1 plus u2 times v2. So how do we compute a dot product? All we're doing is we're multiplying the x component together and the y component together and then adding the two answers up. Right away, what do you notice about the result of a dot product? There's something a little bit different than what we had been doing for all these other vector operations prior to this one.
There's no parentheses.
It's just a number. Notice that this result is not a vector. The result of two, or the dot product between two vectors, is a scalar. This is the first time this has happened. When we add two vectors or scalar multiply or subtract vectors, all of the results were vectors. Here the result is a single real number. It's a little bit similar in Algebra 2, or your algebra course last year, I guess, when we talked about matrices. Remember when we take the determinant of a matrix, the result there is also just a number, right? No longer a matrix. So a little bit similar to that. So let's outline some important properties of dot products. The first one is the commutative property. What that basically just says is that the order you do the dot product doesn't matter, that u dot v is the same as v dot u. Oh, maybe we should say what these things are. So u, v, and w are vectors, and k is just some real number. The next is there's a multiplicative identity property that says 0 dot any, or the 0 vector dot any vector gives us, what do you think? 0, just the number 0. Next is the distributive property. So this says that u dot v plus w is equal to u dot v plus u dot w. And because dot products are commutative, it doesn't matter on which side of the parentheses you do that dot product. The next one is the scalar associative property. That's just kind of the convention that when dealing with vectors, we use those two letters. There's not really a good reason. They're just kind of the two letters that we use as kind of our standard vector variables. Mostly so you're not double using like x, y, and z, so you don't have like potentially x and then the vector x inside of the same problem. What the scalar the scalar associative property says is if I have a dot product that also involves some scalar multiplication, it doesn't really matter when and where I do that scalar multiplication. I can multiply the scalar to the first vector and then take the dot product. I can multiply the scalar to the second vector and then take the dot product. Or I could do the dot product and then multiply in the scalar. It doesn't really matter when you do it. It's going to give you the same result either way. 5. The last one is the magnitude property that says the dot product of a vector and itself is just its magnitude squared. In your homework, you're going to be asked to prove these 5 properties. We're going to do one of them right now. Which one would you like to do?
Number 5.
Number 5.
Never stop speaking words.
Probably 3.
Yeah.
3 or 4. Yeah, which one's hard?
4.
They're all easy.
Bruh.
I mean,
4.
4? All right. Seemed like you...
Yeah, just be safe.
I'm not doing 2.
But you said they were each.
They are, but I don't feel like doing more than 1 because it's stealing from you guys, your practice. Okay, so if we're doing 4, the first thing I'm going to do is designate some variables. So I'm going to call vector u the vector u1, u2. I'm going to say vector v is the vector v1, v2, and I'm just going to say k is any real number. So if I want to show that k times u1 dot v is equal to u dot k times v, which is equal to k times u dot v, what I'm basically going to show is that each one of these 3 gives me the same result. So I'm going to compute each one of those 3 parts and show that they give me the same result. Is everybody okay with that idea? It's a real number. Just a real number, not a vector. Just a real number. Like 7. Okay. All right. So let's just take the first piece. So I'm going to start by just replacing the vectors with their component forms. Then I'm going to do the scalar multiplication. And then I'm going to do my dot product. And because k, u1, and v1, and k, u2, and v2 are all just real numbers, it doesn't really matter what order I do them in, so I can just drop those parentheses. Okay. Now let's look at the second piece. So again, I'm just going to start by replacing these with their component forms. First thing I'm going to do is perform the scalar multiplication. Oops. Now I'm going to do the dot product. And because U1, K, and V1 are all real numbers, it doesn't matter the order I do that multiplication. And similarly, U2, K, and V2 are all real numbers. It doesn't matter the order I do the multiplication. So I'm going to write them in those orders. And what we've done here is shown those first two things are equal, right?
I'm doing WTS, but I can't see WTS.
I don't even know what the difference between you
They're just two separate vectors.
Okay, can you scroll up a tiny bit?
It's property 4 is all I wrote. I just recopy property 4. It's on your paper already.
Is there any way that you could like not use UOB anymore? Use like
Yeah.
a letter that doesn't.
You can change them to whatever letters you want on your paper. I mean, they're definitely two different symbols. The V's have no tails and the U has a tail. I think your eyes need to be a lot more checked.
How about like
Yeah, I wrote you for the whole-
Mr. Cool and
I
like
wrote in front of you.
getting a song
Like that's
where-
not
Yeah.
right.
Yeah, Mr. Cool is
Can we do it with real numbers?
Whoa.
Not a proof.
Oh.
That's not a proof then.
This is like, you go back.
So are we done with it?
No, we still have a third part, but you guys
It was easy.
keep bellyaching.
I'm just so confused. Hey, does anyone
Now we're done.
That wasn't hard at all. So are the right side of these?
See, that's what I'm saying.
I've been writing you for everything. My biggest struggle.
I'm almost done with you. You know what else? The comments with that one.
Yeah, there's a lot of blindness
Yeah.
going on. I think that's the most confusing part. Right. So what did we just do?
We proved property 4.
How?
Okay. How do you show that? So we wanted to show that these three things are equal, right? What I did is I picked an arbitrary value for vector u, an arbitrary value for vector v, and an arbitrary real number. What I then did is I computed this, and I got that. I computed that, and I got the same thing. So what does that tell me?
The third one must be true.
No, that those two are equal, right?
I'm just tired of hearing you guys.
Okay,
Okay, go on.
stop talking. Basic geometry logic. If A is equal to B and B is equal to C, what can you say?
A is equal to C.
That's exactly what we've shown here. This is A, this is B. This is C, this is B. So A and C are equal, right? We did the same thing now. D is equal to B. So now A, C, and D are all equal. That's what we did. Basic, like just basic geometry logic, right? Just the transitive properties, all we use there, right?
Yeah.
Because I had if I want to show three things are equal, if they're all equal to the same thing, they must all be equal to each other, right? That was the proof. That's how you do almost all algebraic proofs, are just symbolically showing the two things are equal to the one side and the other side are both equal to the same thing. So, a numeric example. Okay, so we have vector u is the vector 2, -3. Vector v is the vector -1, 5. Vector w is the linear combination form vector 8i plus 4j. So the first thing I would do is translate all of these vectors to the same form, and I would use component form. So I'm going to rewrite this linear combination vector as a component form vector. What is the component form vector for W? 8, 4.
Wow.
Okay. So now I'm just going to go ahead and plug in the component forms into my problem. So I'm going to just follow my standard order of operations. I'm going to do the stuff inside the parenthesis first. 8 minus 2 is -6. -3 minus 4 is -7. I know from the scalar multiplication associative property, I can multiply this 2 at any point. I'm going to multiply it right now into vector v. 2 times -1 is -2. 2 times 5 is 10. Now I just need to take the dot product of these two vectors, so I multiply the x components together, and then multiply the y components together. So that gives me 12 minus 70, which is -58. And I'm done. So this is an example of just me computing a dot product. Okay. So let's say we were interested in computing the angle between two vectors. So let's say, let's say here is some vector v, and over here is some vector u. What we're interested in then is this vector here, theta. What shape does this look a little bit like? Almost looks like a triangle. Let's make it into a triangle. Okay? So I'm going to draw in this side here as a vector. What name would this vector need to have? What name should that gray vector have? Well, let's think about it this way. So I've written these two vectors head to tail, right? What vector operation does this imply geometrically? That is addition. So the picture we've drawn there is a vector addition. So what is the gray vector's name? Just v minus w. Everybody okay with that?
So that's the name of the.
Yep. Okay. So we have a triangle, and we know something about the three side lengths, and we're interested in angle measure. Do we have a tool that we can use that relates the side lengths of a triangle and an angle measure inside of the triangle?
Yeah. Law.
The law of cosines. So I can say that the magnitude of v minus u squared is equal to the magnitude of u squared plus the magnitude of v squared minus 2 times the magnitude of u times the magnitude of v times cosine theta. That's the law of cosines. Like 8 separate times during my mathematics career. Geometry? Like you guys did?
Did it make sense to you when you learned it?
Yeah.
Just use a mathematician.
Well, I mean, here's the thing with this making sense, is you have to know like the vocabulary and the symbols, and when you're doing your homework, if you're like, what does that symbol mean again? You have to go back and look it up. And then you have to write that down. It's like, hey, I need to memorize what this symbol means. And when you get to some vocab and you're like, what did that mean again? You have to stop and look it up and then write it down as a list of things to memorize when you go and look it up. So like, because if you have to keep stopping and looking back every single time, you can't like learn the next thing. You have to stop and like, okay, I just need to memorize what this stupid symbol means because I've had to look it up now 3 times, and it's now apparently very important. Or I need to memorize what this vocabulary means. And if you're like stuck on something like I don't know what I don't know, you need to come talk to me. And that's really what it comes down to. And because it should make sense when you sit down and do the problems. And I understand that like we move fast. And like sometimes it's hard to keep up, but when you sit down and you do the homework, if it doesn't make sense, then it's time to make sure you're stopping and asking some questions and getting some extra help.
Okay.
But sometimes what we're doing is, like very vocab heavy, and we don't do a lot of specifics. And the homework is very specific. Like what you saw in 1 through 22 was all numeric. It was all just calculations, right? You're just figuring out which formula you needed to do and what exactly you needed to do it, but they weren't difficult problems from a computation standpoint. Nothing took a long time to do. And more or less, that's kind of this first half of this chapter. Nothing takes a long time to do, but you have to understand what the symbols mean and what the vocab means so you know what to do. And that's the place where I think that when you do your homework, that's where you really should focus,
Okay.
Megan.
If your triangle thing was in a different quadrant, so then you have to see it.
So all it mattered was what things were head to tail. So the fact that I drew the tail of the gray vector starting at the head of the u vector means that if I drew it the opposite way, it would just be u minus v. So it doesn't matter what quadrant it's in. All right. Next up, I'm going to use the magnitude property of vector or of dot products. So what that says is the magnitude squared is the same as the dot product of the vector with itself.
Wow.
So I got that.
Wait, is that just extending that equation?
Yeah, I just applied the magnitude property. So it applied here, here, and here. Where the magnitude squared is the same as the dot product of the vector with itself. Okay. Because we have a distributive property for vectors, what can I do with this? Because the dot product distributes, what can I do with that? Foil it. Good.
Yay.
So that's v dot v minus u dot v minus u dot v minus u, plus u dot u. Oh, you know what, guys? Let's not do this.
Oh, thank God.
I'm going to leave those as magnitudes.
Wait.
You guys do so much complaining. This is a really pleasant. This is a pleasant chapter.
It's a cute, yeah.
It's about complaining.
Because it's finally something like
It's about
really new, right? This is like a whole new language.
yes.
Yes, and I take how to speak.
Yeah.
Yeah, that's, hey, look, it's okay to struggle a little bit right now. That's okay.
10 out of 10.
You just have to be patient and like take my advice about when you're doing things, like you got to go back and you have to look up the definitions for things, and you have to look up what the symbols mean again, and then make a note of it so that you go back and like refresh your memory on a regular basis about what those mean. Like make a little glossary of yourself for yourself of like, hey, what does this mean? How do you, like a little cheat sheet that you can keep referring back to so that you memorize these things. Well, no, I mean you have to have them memorized by the test, but like that, you know, it's not going to, because it's a completely new language. It's not like when we just write something down like 5 plus 6 and everybody immediately knows how to do 5 plus 6, right? If I write vector v plus vector u, you immediately don't know what those things mean, right? All right, so I'm going to use the magnitude property again, here and here. And now good things are starting to happen. If I subtract the magnitude of v squared from both sides, those canceled out, right? The goal is we're trying to figure out that angle theta, the angle between the two vectors. If I subtract the magnitude of u squared from both sides, those cancel out. Everybody okay there? Gabe.
So, like, are we kind of just showing how we do it in another?
We're going to end up with a formula. Yeah, exactly.
Oh, so this isn't the step we take for each one.
No. We're doing the hard step once so we can use the shortcut from then on.
Oh,
So we're literally just getting down to a basic formula.
Yeah.
That we can use for this. type of-
Yes.
So this is
We
the
thought this was the
derivation.
Oh my God.
This is the derivation or whatever you call it.
Mr. Kulik,
It's exactly what we're doing.
you should
Oh
mention
my
that.
God, we're trying to.
Are you kidding me?
And then
Oh,
we're almost done. We divide both sides by -2 magnitude of u times magnitude of v. And the -2's cancel. And then if we take the cosine inverse of both sides,
wow.
we're left with a formula now that'll take us directly to the angle between two vectors.
Now we're starting.
So if I want the angle between two vectors,
Yeah, just to get it. Yeah.
we're going to use this formula that we just developed. Okay?
angle measure was
Find the angle measure between
Oh,
vectors u and v.
I'm kind of.
Sure, you can use whatever shorthand you want to use. All right. So to use this formula, I need three things. I need the dot product of u and v. I need the magnitude of u. And I need the magnitude of v.
So is that something?
Well, I mean, all I'm doing is saying this piece, and this piece from my formula. I'm just doing it as like some separate steps, so it's less messy.
Good idea.
So if I do these two dot products, I multiply the dot product of these two vectors, I multiply the x's together and the y's together, and then add them up. And if I calculate the magnitudes, I get square root of 85 and then the square root of 8. So I take the cosine inverse of 2 over the square root of 85 times the square root of 8. What mode should my calculator be in? Good. Degree mode. And I get 85.60. That's it.
That huge derivation for nothing.
I can.
Okay.
Thank you for
Now, when we talk about angles, what angle measure would you say is probably the most important angle measure? 90. Great. Yeah, so we're especially interested in if two vectors have a 90-degree angle between them. Okay, we're going to give that a special name. We're going to call those two vectors orthogonal. is that AL. So we say two vectors are orthogonal if and only if their dot product is 0. Orthogonal just means the angle between the two vectors is 90 degrees. So suppose I want to show that -5/8 and 16/10 are orthogonal. What would I do?
You're gonna multiply 5 times 16.
Yeah, we're going to take the dot product. And we get 0. Are we okay with that idea? So again, when it comes to the computation is very easy, right? You just take the dot product, and if you get 0, they're orthogonal. If you don't get 0, they're not. Easy peasy. No, we still have 15 minutes left. I can't burn 50. Look, I want to be very honest with you guys. There's going to be days where we're not going to do a lot in this chapter. That doesn't happen already. We have not gotten to the things that are actually time-consuming and really difficult. And I want to make sure that we have time to really spend on those parts. To do that, though, we can't stop and take 15 minutes here and there on these things that are largely okay, Gabe. I understand that you feel overwhelmed right now, and I really do. I'm letting you know that based on the kinds of questions you guys are asking from the homework and the limited questions we ask from the homework, I don't think it's as bad as you feel. Okay, those of you that didn't do the homework, that's part of the reason why you feel super overwhelmed. Okay, is that you didn't have a chance to practice any of the symbols or the vocab, so you feel behind. That's part of what's going on. Everybody take a deep breath. It's going to be okay. We are going to stop and slow down and practice things and give you a chance to get better at these and ask questions and work on the homework and those sorts of things. That can't happen right now. I hear what you're telling me. I really do. And I'm telling you that we are going to do that, but it needs to happen a little bit later.
Oh, I love it.
Yes.
Love to
So
see it.
excited.
So a boat leaves a port and averages 40 knots for 2 hours on a course of 215 degrees. Then the boat turns at a bearing of 162 degrees at 55 knots for 3 hours. What is the distance and bearing of the boat relative to the port? So, how many vectors are described in this problem? 2. 1 for each leg of the boat's journey. So let's draw a picture for the first vector. Okay. So it says a course of 215 degrees. Remember when we draw the angle for courses and bearings? Where do we start our angle at?
X-axis on the right.
The north.
Oh,
And which way do we rotate?
right.
Clockwise.
So, right.
So 215 degrees, here we're 90, 180, and like 35 more is here. And if I call this vector, say vector v, the magnitude of vector v, the length of it, is going to be 2 times 40, or 80, right?
Um,
40 knots for 2 hours. You go 80 nautical miles or whatever. But to translate this to component form, I need this standard position angle theta here. What is that angle theta going to be? Well, it's going to be 180 plus 55. So we can say V is then 80 times cosine 235, comma 80 times sine 235. If you want to convert that into decimals right now, you could. I'm going to leave it in exact form. I'm going to draw my other vector. So it says this one goes on a bearing of 162 degrees, so 90, and then like 72 more. I'm going to call this vector vector u. So we know the magnitude of vector u is 3 times 55, went 55 knots for 3 hours, so 165 nautical miles. But again, we're interested in this angle theta. So theta here is going to be 360 minus 72, or 288. So we can say that vector u is 165 cosine 288, comma 165 sine 288. Everybody okay there? Well, this is the second time I've done this today, but it's also, I'm just fast at things. I don't know about the best. I make lots of mistakes. You guys have seen it. Okay. So the vector that I care about then at the end is going to be the vector u plus v. So that's just going to be 80 cosine 235 plus 165 cosine 288, and then 80 sine 235 plus 165 sine 288. And if I convert that into a fraction, or I'm sorry, to decimals, that's 5.10 negative 22246. So that's the ship's final position. So I just need now to squeeze out of that a magnitude and direction. Actually, magnitude and bearing, I think, is what the problem asked for. Okay. So the magnitude of this, well, since I'm in component form, I can just use my magnitude formula for a vector in component form. To give me 222.51 nautical miles. And then if I want to find the bearing, start by drawing a picture. So I'm going to plot the point 5.10, negative 22246, which is going to be like a vector there. I'm going to then resolve that vector into a triangle, where the sides of that triangle are 510 and 222.46. So this angle here that I'm going to refer to as alpha is tan inverse of opposite over adjacent. And that comes out to be 88.69 degrees. The angle that I'm interested in is the bearing. So that's going to be 90 plus alpha. So that's 178.69 degrees. So there's my bearing, and there is my distance. Just like what we did in first semester when we dealt with these problems, right? We just were a little bit more explicit about using vectors in component forms and showing the vector addition, but the procedure is not different than what we did first semester, right? We're going to stop here because the next topic is quite lengthy, and there's no way I can make a dent into it in 5 minutes. So I can stop here. For next time, what I'd like you to work on is 23 through 40.
You guys, you know, there's 122,000.
What? There's not.
Probably. There's like, how many sections are there in this chapter, though?
Wait, how many are there?
8.
Okay, could we like split it up? Somehow?
We can take home.
Can we do a take
Take home is a really good
No,
idea.
I don't want to take home.
That's a great idea.
Take home such.
Okay.